Hello everyone. Welcome to the Machine Learning Teach by Doing Lecture 10 or the Day 10. Today, I am incredibly excited because today we are going to learn about one of the oldest machine learning models which was actually developed in 1957. The name of this model or algorithm is the Perceptron algorithm. The name sounds pretty cool. And today we are going to learn all about the Perceptron algorithm right from scratch. As always, I'll be presenting with a whiteboard approach where I'll be writing everything in front of you so that you completely and clearly understand this algorithm. Let's get started. Before that, in the previous lectures, we looked at linear classifiers and we looked at another algorithm called as the random linear classifier algorithm. Today we are going to look at the perceptron algorithm, which is a bit more smarter than this random linear classifier algorithm, which we looked at before. So if you have not seen the previous lectures, please go through this to get a feel of this algorithm so that today when you learn about the perceptron, you will appreciate it much, much more. So as I mentioned, the perceptron algorithm is one of the oldest machine learning algorithms. It was invented in 1957, which is almost around 60 to 70 years back. And today we are going to learn about that. In fact, this was not just a model, it was also implemented as a machine by engineers. And here is how that machine actually looked like. So, this is the machine on which the perceptron algorithm was implemented. It's also called as the Mark 1 perceptron machine, which was the first implementation of the perceptron algorithm. Here is the person also who is working with the machine. And the main purpose of this machine was to mimic the way the human brain processes visual information and learns from it. Remember, at that time, neural networks and artificial intelligence was not developed at all. In fact, there was no research or no, this terminology itself was not known that AI can represent the human brain. So the researchers who developed the perceptron algorithm, they had this insight that what if we can mimic the way the human brain processes visual information. The perceptron is very fundamental and very rudimentary, but this gave the idea to the fact that ML algorithms can essentially represent what's happening in the human brain. So when the perceptron paper was released, here you can see the authors mentioned this in the figure, that in figure 1 they showed the organization of a biological brain, and in figure 2 they showed a organization of a perceptron, and they visualized a world in which we can have ML algorithms like the perceptron which can model the human brain. This is the algorithm from where the idea or the concept of artificial intelligence was really born, and today you are going to learn about it. So imagine that you have a time machine which takes you back 60 years and you are learning about the first ML algorithm. The reason I am teaching this to you right now is because to appreciate all the current algorithms, you will see that the roots of the current developments lie in the past, as is the case with so many things. So it's very important to appreciate the historical ML algorithms so that you don't feel intimidated by the new ML algorithms. This was actually one of the first models which could learn from its mistake. Remember, at that time, the idea of machine learning was not really invented. But now, if you think of it, a model which could learn from its mistake is essentially the key idea behind machine learning itself. In machine learning, also, the machine is learning as it interacts more and more with the user. So the perceptron algorithm was one of the first model which could learn from its mistake. So in essence, it was one of the oldest machine learning models. When the algorithm itself was developed, the primary aim of the perceptron was to be able to recognize shapes, patterns, letters, and numbers. Now we can do so many more things, but at that time it was revolutionary because it could learn from its mistakes on its own without human intervention. So let's get started. As I mentioned, this will be an interesting hands-on lecture in which we will completely understand the perceptron right from the very basics. I won't ever use a terminology or just show you something on the screen which I myself have not written down. Um, that way you can easily understand what I'm doing and what I'm writing. So let's get started. One more thing before we get started is that this particular lecture is inspired from the MIT's Perceptron lecture. The Microsoft lectures, as I mentioned, they are heavily geared towards practical aspects, so they don't have anything about the perceptron. This is another again one of the reasons. If you take courses which are fully just practical, you will miss out on these brilliant historical ML algorithms, and you will miss out learning about them. So let's get started with understanding the perceptron and learning all about the perceptron. So, okay, first of all, the first thing to note is that the perceptron is essentially smarter than the random linear classifier, which we looked at before. So do keep this in mind. Secondly, perceptron is also an ML algorithm which gives us the best linear classifier. So the problem which we will be looking at is the same one which we looked at when we constructed the random linear classifier, and I will introduce the problem to you, don't worry. So let's introduce the problem. We have x1 and x2. X1, which is the x-axis variable, is whisker length. So we are collecting a bunch of dogs and cats. We are measuring the whisker length, and we are measuring a metric which is called as the ear flappiness index. Okay. So the dogs will be called as the plus category, and the dog data looks something like this. So as you can see, dogs generally have higher ear flappiness index but lower whisker length. So this is the data for the dogs, and the cat data looks something like this. Cats generally have essentially a higher whisker length but a lower ear flappiness index. So this is how the cat data actually looks like. So the goal of the perceptron algorithm is actually to find the straight line which best separates these two data. That's the goal. And in two dimension, the equation for the straight line will be theta 1 x1 plus theta 2 x2 plus theta naught equal to 0. So first let us look at the perceptron algorithm itself, and then I will explain to you every single thing in the algorithm step by step. So let us look at the perceptron algorithm. Okay. So I'm going to call this algorithm as perceptron, and the inputs which it takes are D and T. D is the training data and T is the hyperparameter. We will explain what T is in the subsequent lectures, but today the main goal is to not focus on T but to really understand the algorithm itself. So initially what I'll do is I'll initialize theta and theta naught to be equal to 0. One more representation which I'll follow continuously throughout this particular uh, lecture is a vector notation. So remember that when I write theta here, this is a vector, and not just so theta is equal to theta 1 and theta 2. So remember, ultimately we have to find the parameters theta 1, theta 2 and theta naught, right? What I'm going to do is that I'm going to represent theta as a vector which has two values, theta 1 and theta 2. Theta naught will remain to be a scalar. So if I find theta and theta naught, I just have to take the first value of this vector, that will give me theta 1. I'll take the second value of this vector, that will give me theta 2, and then essentially I'll find this straight line. So this is the vector notation which I'll be following throughout this course, or rather throughout this particular lecture. Now here is where the algorithm actually starts. For t equal to 1 to t, 1 to capital T. So remember, this is the hyperparameter. For now, just keep in mind that we are going to do capital T iterations or capital T loops. And within this, there is actually one more loop. For I is equal to 1 to n. And n here is actually the number of training examples. Number of training examples. Don't worry if this notation is seeming complicated to you. We will take a hands-on example and completely explain in detail. So this is how the algorithm proceeds. Then comes the important step. If so, here we are basically saying that we go through every training example step by step. So first we go through this example or the training data. Then we go through this training data. That is what is meant by I equal to 1 to n. So you go through each training point step by step and you check this condition. If y, which means the label of that particular training data point, into theta transpose xi plus theta naught is less than or equal to 0, update theta to theta plus the y label multiplied by the x, and update theta naught to theta naught plus yi, and then after all these loops are done, the values of theta and theta naught which you get will be your optimized separator. This is what the perceptron algorithm is. If you see, the length of this algorithm is 1 2 3 4 5 6 7, just 8 lines, but there are a lot of things going on within this. The first thing to notice is this: there are two loops here. There is a there is a loop number 1 which will do capital T iterations, and then there is the loop number 2, which means that we will go through every single point in each iteration which we are doing. So for each of the capital T iterations, we will go through each of the point and we will check whether this condition is satisfied or not. If the condition is satisfied, or if it's less than or equal to 0, we will update theta and theta naught, and we'll keep on doing this until the loop stops. What the perceptron algorithm tells is that at the end of running the algorithm, whatever updated theta and theta naught remain at the final step, those will be my optimal theta and theta naught, and that will give me my straight line. This is the perceptron algorithm, and in the rest of the lecture, I'll be going through each of these sentences step by step. One more notation which I would like to clarify with before moving forward is theta transpose x. So what this means is, this is a vectorized operation. So this actually means theta 1, theta 2 multiplied by x1 and x2. So when I say xi, it means x coordinate and y coordinate. So theta transpose xi is actually just theta 1 x1 plus theta 2 x2. This will come up at multiple times, so even if you are not familiar with linear algebra, it's fine. You just need to know this particular transpose notation right now. And now let us go through understanding everything step by step. So let me write here, what does it mean and how does this work, why does this work? I'm sure all of you must have so many questions. So let me clarify the questions step by step. So let us understand. The first two statements are pretty easy to understand. Initially, the algorithm states that we start with 0. So initially you start with theta 1 equal to 0, theta 2 equal to 0, and theta naught equal to 0. That's fine. then these two loops are also easy to understand, that you do capital T loops, and in each loop you go through all the training points step by step. But the real thing which I want to right now show you is, what does this mean? So what does this actually mean? uh, and when I say it, I mean yi into theta transpose xi plus theta naught. What does it mean when we say that check this condition? So this is the condition which we are checking here, right? So what does this practically mean? So let us understand this visually. For that, again, I'm going to construct the x1 and x2. So remember that these are the two classes which I want to separate, and the positive class, which means plus. So the label can be +1 or -1, right? So let's say the dog data will now have the label as +1, which means that for all of these values, or for all of this x1 and x2, the answer is equal to +1. And for all of these x1 and x2, the answer is equal to -1. So just remember that in our previous thing which we started with, this example, +1 corresponds to dog data and -1 corresponds to cat data. So all of these points here which are dog data, their true y value is equal to +1. So essentially, the what it means is that for all of these points with their given whisker length and ear flappiness index, the answer is +1, which means that they are a dog. And for all of these points, the answer is the true answer, which is called true label. The true answer is -1, which means they are cats. Now let us see what each of these things mean. First of all, theta transpose xi plus theta naught, that is the current hypothesis, right? So this is just theta 1 x1 plus theta 2 x2 plus theta naught. So as the perceptron algorithm is running, this is the current hypothesis at that particular iteration. So this thing which I have currently marked as orange, maybe it's the current hypothesis. So this is the current hypothesis. And out of which xi is the current data point which we are looping through. So remember that we are going to sequentially go through every single training example, right? So let's say for the purposes of this illustration, this is that example which we are going through. So for this particular example, we have certain xi and yi is equal to +1. This is yi because it belongs to the dog data. So yi is equal to +1 and we have some data. Okay. Now, let us see what does this mean. Why I am multiplied by theta transpose xi plus theta naught. Uh, but before that, I want to focus on theta transpose xi plus theta naught itself. Like, can we visually understand what theta transpose xi plus theta naught actually represents? So there is a beautiful visual understanding of this. So let's say this is our current hypothesis, right? And this is our normal. Let's say this is the origin, this is the normal vector. So theta transpose xi plus theta naught actually represents if the point is on the positive side of the normal or if the point is on negative side of the normal. Essentially, let's say if you take a point on the positive side of the normal, then theta transpose xi plus theta naught will be positive. If you take a point on the negative side of the normal, theta transpose xi plus theta naught will be negative. So, what theta transpose xi plus theta naught actually tells us is that is xi on the positive side of the normal or negative. Right. So let's say, so this is our hypothesis, and if we put xi into this hypothesis, and it turns out that theta transpose xi plus theta naught is greater than 0. So let's say if our current hypothesis, if we plug in xi into our current hypothesis and it turns out this is equal to 0, it means that xi is on the positive side of the normal, which means that our hypothesis will predict of normal. Our hypothesis will predict plus 1. And if this is equal to less than 0, so then our hypothesis will predict minus 1. So when you think of theta transpose xi plus theta naught, it actually represents whether xi is on the positive side of the normal or if it's on the negative. And remember, if something is on the positive side of our hypothesis, it is classified as plus 1, and if something is on the negative side of our hypothesis, it is classified as minus 1. So this value actually tells us if this value is greater than 0, our hypothesis will classify that point as plus 1. If this value is less than 0, our hypothesis will classify the value as minus 1. One more way to actually visually understand this particular point is through a vector representation. So let's look at this particular point here. So let's say this is the vector from the origin to that particular point, this vector, and this is the normal vector, right? So theta transpose xi plus theta naught actually just represents the dot product between these two vectors, which means that if there is an acute angle between these two, theta transpose xi plus theta naught will be positive, right? Whereas if there is an obtuse angle between these two, like for this point, then theta transpose xi plus theta naught will be equal to negative. So if you visually want to inspect what our hypothesis predicts, so let's say orange is my hypothesis, right? And visually I want to predict what my hypothesis predicts for this particular positive point and this particular negative point, right? The way to do this is look at the normal of the hypothesis, it's here, and draw the vector first from the origin to this point and then to this point, and then look at the two angles. So this angle will be called as theta 1, and this angle will be called as theta 2. So theta 1 is acute, right? Which means that my hypothesis will classify this point as positive. And theta 2 is obtuse, which means that my hypothesis will classify this as negative. So the only conclusion from this segment is that theta transpose xi plus theta naught actually tells us the classification of that point made by our hypothesis, not the true value. The true value is already fixed. For all these points, the true value is plus 1. For all these points, the true value is minus 1. So if theta transpose xi plus theta naught is greater than 0, our hypothesis will predict plus 1. If theta transpose xi plus theta naught less than 0, our hypothesis will predict minus 1. Now, with this understanding, let us try to understand what does this represent? Why I multiplied by? So, what does this represent? Why I multiplied? Okay, let me. So, we saw theta transpose xi plus theta naught, right? And its meaning. So, now let us see what is the meaning of why I multiplied by theta transpose xi plus theta naught. Okay. So, for that, I am going to construct a table. In this table, if we are right, and you will understand what I am writing here, if we are wrong. And when I say we, I mean our hypothesis. and the third thing is multiplied by, so the multiplication of first two columns basically. Okay, now let us actually understand what the product means. So let us look at this point which we have already highlighted here. It's true yi is plus 1, correct? So it's true yi is plus 1, which is plus 1. So if we are right, which means that our hypothesis prediction is correct. Remember that uh, theta transpose xi plus theta naught is essentially predicting whether our hypothesis will predict plus 1 or minus 1, right? So if we are right, which means our hypothesis will predict that theta transpose xi plus theta naught is greater than 0, correct? So if we are correct, our hypothesis will classify this point correctly. So our hypothesis, so this will be greater than 0, right? Remember what we have written here. If theta transpose xi plus theta naught greater than 0, hypothesis will make the prediction as plus 1. Whereas if theta transpose xi plus theta naught less than 0, hypothesis will make prediction as minus 1. So the first row is if we are right. So if we are right, the correct prediction is plus 1. So our hypothesis should make a prediction of plus 1. So it should be greater than 0. If we are wrong, our hypothesis will predict minus 1. So then this should be less than 0. Now look at this product. In the first case, the product will be positive. In the second case, the product will be negative. Did you understand this product basically? Basically, if you take any particular point xi, and if our hypothesis is right for that particular xi, the product of yi and theta transpose xi plus theta naught will be greater than 0, as we have seen here. So if the hypothesis is right, the product of yi into theta transpose xi plus theta naught greater than 0, and if the hypothesis is wrong, then the product of yi into theta transpose xi plus theta naught will be less than 0. So essentially what this represents, uh, what this product actually represents is that if our hypothesis is right, then yi multiplied by theta transpose xi plus theta naught will be greater than 0. Whereas if our hypothesis is wrong, then yi multiplied by theta transpose xi plus theta naught is less than 0. The way to simply understand this is that, okay, if the correct answer is plus 1, then this thing will predict, our hypothesis will predict plus 1. So then yi into this will be positive. But if the correct answer is plus 1, and if we want our hypothesis to be wrong, the correct answer will be plus 1, but our hypothesis will predict minus 1. So then this product will be less than 0. That is the significance of this product. So essentially what this algorithm is saying is that here we check whether our current hypothesis has made a mistake or not. That's it. So essentially at this point we are saying that if our current hypothesis is less than or equal to, if this product is less than or equal to 0, which means a mistake has been made. So let's say we have a hypothesis and the current point which we are testing is some point. What this line says that if we see that our hypothesis is making a mistake, then you need to update theta and theta naught. Whereas if we see that our hypothesis is correct, then that's it, go to the further iteration. You don't need to update anything. That's all which is being mentioned by this particular syntax here. So just to specify or just to write or drive this point home, in the algorithm what this so checking this statement actually means. So checking this statement means that if it's a mistake, then update theta and theta naught. If this is greater than 0, then we are happy, just move to the next point. Now let us look at the updating part. So up till now we looked at the meaning of this particular part, right? What does this product mean and what does it mean if the product is less than 0? We saw that the product being less than 0 means that our current hypothesis has made a mistake on that point, and then we need to update theta and theta naught. Now we are going to look at this update in detail. So the update is basically, so if there is a mistake, we update theta and theta naught, right? And in the algorithm, this update is given as theta is equal to theta plus yi times xi, and theta naught is given as theta naught plus yi. Now, if you see any other course out there or any other videos, they have not given the intuition behind this update at all. What is the intuition behind this? Does this just magically work? That did someone come up with these updates in 1957 and it magically works? No, there is actually a very beautiful implementation or a beautiful intuition behind why we need to update theta and theta naught if our hypothesis has made a mistake. But I want to come to that towards the end. But first, I want to make sure that I have not lost you in the process. And so, whatever I have just mentioned up till now, this multiplication and this hypothesis, this algorithm, I actually want to take a functional example and want to show you exactly through this functional example how the perceptron algorithm actually works. So, let's go ahead and start looking at that example. So, this section I'll be calling perceptron in action. Let me open my notes to that particular page. Correct. So this section I will call as perceptron in action. Perceptron in action. And as always with practical demonstrations, let's construct a XY grid and look at a very nice demonstration. Okay. I know my drawing is a bit not very good, but trying my best. So this is the origin point 1, 2, 3, -1, -2, -3. Here again it will be -3, -2, -1, 1, 2, 3. So, okay. So the first point which we are going to take. So first let me draw the positive points. The first positive point is -2, comma 3. So this is positive, and this is -2, comma 3. The second positive point is 0, comma 1. 0, comma 1. And the third positive point is 2, comma -1. 2, comma -1. And now I am going to take the negative points, which means the points whose actual value is -1. So the first negative point is -2, comma 1. -2, comma 1. The second negative point is 0, comma -1. So it's here 0, comma -1. and the third negative point is 2 comma minus 3. So this is the third negative point. Great. So now I will run the entire perceptron algorithm for these set of positive and negative points, and I will show you how it leads to the convergence of the results. So let us run the perceptron. Let's run the perceptron. Great. So let us look at the steps above. The first step is start with 0. So everything will be initialized as 0. So remember theta will be equal to 0 comma 0 and theta naught will be equal to 0. Okay. Then what it says is that so for this example, I will just do one loop of this hyperparameter. So let's forget the first loop and let's come to the second loop. What it says is that we have to choose a training example and then go through each training example step by step. So first let us look at the training example, which is this point minus 2 comma 3. So let me write it with orange. The iteration 1 which we are going to do is for the point xi is equal to minus 2 comma 3. Okay. And now what this tells us is that, okay, once you have chosen the xi, you find this value yi into theta transpose xi plus theta naught. So let us try to find this value. uh, Let us try to find yi multiplied by theta transpose xi plus theta naught. So then this will be equal to, so the y value which is the true value for this point is equal to plus 1, right? So then this will be equal to plus 1, plus 1 theta transpose, which means the current theta is 0 0, so it will look like this, and the x is minus 2 comma 3 plus 0, because the current theta naught is 0. So this will just lead to 0, so this product is equal to 0. But remember that there is a less than or equal to 0 sign. Less than or equal to 0, so we have to go to the next iteration. So this is another important point. Whenever the perceptron starts for any data set, since theta and theta naught are 0, it will always make a mistake initially. It will always satisfy this condition, and so by default we will have to update theta and theta naught. So then let us update theta and theta naught. So then the updated theta is equal to the original theta plus yi into xi, which is equal to 0 plus yi is equal to plus 1 and xi, which is the point coordinate, is minus 2 and 3. So my new theta will be equal to minus 2 and 3. Minus 2 and 3. And theta naught is equal to theta naught plus yi. And since theta naught is 0 and yi is equal to 1, this will be my new theta naught. So this is my updated theta and this is my updated theta naught. So the first updated line, so remember we started with 0, right? So it is difficult to show that line on the map, but we can definitely see the first updated line on the map. This is theta transpose xi plus theta naught. So our theta is minus 2 and 3. So theta transpose x1 x2 plus 1. is equal to 0, which actually is minus 2x1 plus 3x2 plus 1 is equal to 0. So this is the first answer which is given, or the first iteration answer which is given to us by the perceptron algorithm. And let us see how it looks like in this plot. So the first answer given by the perceptron is minus 2x1 plus 3x2 plus 1 equal to 0. And if you plot this, it will actually look something like this. If you plot this line, it will actually, and I highly suggest you try this exercise at home. If you plot this line, it will actually look something like this. This is L1. Now let us analyze L1 for a bit. We can clearly see that it has made mistakes, right? This point is mistakenly classified as positive, and this point is mistakenly classified as negative. So clearly the line L1 is not correct. But the perceptron, this is just the first iteration. We have to still go to subsequent iterations, right? Now the perceptron, what it says next is that this is just for the first point which we did right now, but then we have to iterate for every single point. So now let us choose the second point. Let us choose the second point to iterate as 2 comma minus 1, which is this. And this is where I want to show you right now that there is a this point has been classified incorrectly, right? Which means there is a mistake. So let's choose this point. Now we will go to iteration number 2. And in iteration 2, we are going to choose the point which is 2 comma minus 1. Now here is where I want to show you a trick. As we did before, the perceptron tells us to evaluate this multiplication. Yi multiplied by uh, theta transpose xi plus theta naught. Now let us use our understanding of what we learned in the previous section, right? We learned that multiplied by theta transpose xi plus theta naught just says whether our current hypothesis is making a mistake or not on the point which we have chosen. So this is the point which we have chosen, and this is our current hypothesis L1, right? Whose normal is in this side, whose normal is over here. So this hypothesis will put all the points here as positive and all the points here as negative. Now let us look at this point. This point appears on the other side of this normal. So the current hypothesis will classify this point as minus 1, which is wrong. So that is why this product will of course be negative. You don't even need to evaluate it. You can directly move to the next updating theta and theta naught. But just for the sake of evaluation, I'm just going to show it once. So yi for this particular point is positive, is plus 1, the true value. So this is equal to plus 1, and then this multiplication will be theta transpose xi plus theta naught. So the last theta which we finalized was minus 2 comma 3. So then theta transpose here, this will look like minus 2 comma 3 multiplied by xi, which is 2 and minus 1 plus theta naught. So the last theta naught which we finalized in the last iteration was 1. So this product is actually equal to minus. So this multiplication, if you are not familiar with matrix multiplication, it's fine. You just have to multiply this first element of this row with the first element of the column. So this is minus 4, and then multiply the second element to the second element, and then add both. So minus 2 into 2 is minus 4, 3 into minus 1 is minus 3. So adding these up will give minus 7, and if you add 1 to it, it will be minus 6. So it is less than 0, as we had already predicted. So actually we did not need to do this computation, because if your intuition is correct, right, the intuition says that the product will be negative if the hypothesis has classified our point wrongly. And we clearly see that hypothesis is on the other side, the point is on the other side of the normal. So the hypothesis will classify this point as minus 1, which is a wrong classification. So it is classified wrongly, and then again we have to update theta and theta naught. So then the updated theta will be theta plus yi into xi, which is equal to the current theta is minus 2 comma 3 plus yi. So yi, which is the actual value, is 1 into xi, and xi is 2 comma minus 1. So the new theta, or the latest updated theta, is 0 2, and theta naught is equal to theta naught plus yi. So our earlier theta naught was 1. So and yi is equal to 1. So it will be 1 plus 1 is equal to 2. So the second updated line, which is L2, will be equal to the updated theta, which is 0 comma 2, 0 comma 2 times x1 x2 plus theta naught. So this will lead to 2x2 plus 2 equal to 0. This is the second updated line as given by the perceptron. And let us see how this line looks like. So 2x2 plus 2 equal to 0 actually looks something like this. So it actually goes through these 2 points. So my drawing is a bit, it actually goes through these 2 points, these two, and it looks something like this. This is the normal. Okay. Now, what we are going to do is we are going to take the next point as minus 2 comma 1, and I already want you to guess whether L2 will make a mistake on this point or not. Remember, this is our current hypothesis L2, and again if we choose this point we will need to check yi multiplied by theta transpose xi plus theta naught. So can you tell me whether L2 will make a mistake on this point or not? If please pause here if you are watching the video later, and let me tell you. So this is the positive side of the normal, right? So every point which lies to the positive side, L2 will classify as plus 1, and minus 2 comma 1, this point lies on the positive side of the normal. So L2 will classify this point as plus 1. So of course a mistake has been made. So L2 will make a mistake on this point. So we already know that that product will be less than 0. So we can skip the evaluation step there. So let me show you what I mean. Now we go to the third iteration as we discussed. And this is the iteration 3, in which the point we will be choosing is minus 2 comma 1. And as we did with the previous points, we will have to evaluate the product yi multiplied by theta transpose xi plus theta naught. Now, this is where the trick which I mentioned, we will not evaluate the product mathematically this time, because we already know L2 will make a mistake on this point. So this will be less than 0, and you can check it mathematically when you are doing it on your own. I even have it in my notes, by the way. So you can refer to my notes. So this will be less than 0. So then we'll have to update theta and theta naught. So theta will be is equal to theta plus yi multiplied by xi, which is equal to, remember our old theta in the previous iteration was 0 2 plus, and the yi for this point is minus 1, because remember the true value for this point is minus 1. So then it will be plus minus 1 into xi. The xi is minus 2 comma 1. So then the updated theta will be 2 comma 1, and the updated theta naught will be equal to theta naught plus yi, which is equal to 2 plus minus 1, which is equal to 1. So then our L3, which is the third updated line, will look something like 2x1 plus x2 plus 1 is equal to 0. This is our third updated line given by the perceptron. And let me show you how this actually looks. So, uh, where is that in my notes? So, I'm just checking for L3 in my notes. Right. So, 2 2x1 plus x2 plus 1 equal to 0. So, it will pass through 0 comma minus 1. It will pass through this point and it will look something like this. And here we can see that it is now getting a bit better, but it actually passes through 0 comma minus 1. So that's not the best thing, right? Uh, we ideally need a separator which is kind of a bit distinct. Also, let us look at the points on which this line makes mistakes. So if we look at line 2x1 plus x2 plus 1 equal to 0, it passes through 2 points. Actually, it passes through this point which is minus 2 comma 3, and it also passes through the point 0 comma minus 1. So that is a bit of a problem because it does not seem to be the best separator at the moment. uh, so what we'll be doing is that we will be having one more round of iteration to come to the next point. And let me show you how that uh, iteration looks like. So ideally the best line should not pass through anything. Ideally the best line should be a clean separation between the positive and the negative, right? So currently the problem is that the line uh, which we have constructed, it's kind of basically passing through 2 points. It's passing through minus 2 comma 3. So let me mark L3 here. So it's passing through minus 2 comma 3 and it's passing through 0 comma minus 1. So that's not good. uh, so anyway, perceptron will not allow us to stop there, because if the line passes through some points, this product will be 0. And even if it's less than or equal to 0, we have to continue updating theta and theta naught. Remember, this is less than or equal to 0. So if the straight line passes through some point, our perceptron will not allow us to stop, because this condition will be satisfied and then we'll need to update theta and theta naught once more. So now I'm going to be doing the final iteration, and the final iteration will be on the point 0 comma minus 1. This point, which is whose correct value is actually minus 1, it will be this point. And this point passes through the line. So so yi into theta transpose xi plus theta naught will be 0. So the less than or equal to condition will be satisfied. Remember, theta transpose xi plus theta naught is 0 if xi lies on the hypothesis. So let us come to the similar calculation as we did. Great. So in the iteration number 4, the point which we are going to be looking at is 0 comma minus 1. Okay. And let us look at the product like we do always. Yi times theta transpose xi plus theta naught. So we know that it passes through the line, but let me compute this in front of you just to show you. So yi will be equal to minus 1. And remember, the theta which we finalized in the last uh, iteration is 2, 2 and 1. So then theta transpose xi will look like something like this: 0 comma minus 1 plus theta naught is equal to 1. So if you look at this product, 2 into 0 is 0, plus 1 into minus 1 is minus 1. So this will be equal to minus 1, and then minus 1 plus 1 will be equal to 0. Great. So then the less than or equal to condition is satisfied. So we will have to update theta and theta naught. So the updated theta is theta plus yi times xi, which is equal to 2 comma 1, which was the theta in the previous iteration, plus minus 1 into 0 comma minus 1, which is equal to 2 comma 2, and theta naught will be equal to theta naught plus yi, which is equal to 1 plus minus 1, which is equal to 0. So the L4 will be 2x1 plus x2, 2x1 plus 2x2 is equal to 0. And now let us look at plotting this line. How does this line actually look like? So this is 2x1 plus 2x2 equal to 0. And if you plot this line, let me actually plot it with another color just to show you the difference. To plot this line, if you plot this line, you will see it looks something like this. So it completely separates the positive points from the negative points. You see, this is the first negative point, second negative point, third negative point. All of them lie on this side of the normal. So the normal to this line is this. And all the plus points lie on the positive side of the normal. So they are classified correctly. All the minus points which are in green lie on the negative side of the normal. So they are also classified correctly. So this is our perfect answer, L4, which the perceptron has finalized after 4 iterations. So the final answer which we get to is 2x1 plus 2x2 is equal to 0. And this is the optimal line given by perceptron. Do you see why it is called as machine learning here? I am doing these iterations in front of you manually, right? But when you feed this algorithm to a computer, when you feed this algorithm to a computer, the computer will do all the steps on its own. So essentially, when a computer makes a mistake, which is mentioned by this step, if a computer makes a mistake, it will update theta and theta not on its own, and then it will keep on proceeding. Which means that essentially the computer is learning from its own mistakes, right? That's why the perceptron is an example of a very smart machine learning model. It was the one of the earliest ML models. It was one of the earliest ML models because it learns on its own when it makes mistakes. Like we made so many mistakes here, and we updated theta and theta not every single time, right? So updating theta and theta naught is the machine learning, and then ultimately it gets to the perfect answer. The reason it's much more intelligent than, let's say, the random classifier algorithm which we saw before, something like this. Here we are not learning anything. What it's doing is just we just try 100 different choices and we choose the one which is the best. There is no learning happening here. But I love the perceptron because it's very old. It's 1957 algorithm, and still illustrates beautiful things about machine learning. It's the 1957 algorithm, but still it shows how machines learn. When many developers, many students, they directly jump to the modern algorithms, but they don't write these equations on their own, and they see how the machine learns for themselves, or machine learns itself. I highly encourage you to write these equations on your own and check how the perceptron learns, or how the machine updates itself. Then you will truly understand the foundations of machine learning. This is what I mean by foundational understanding of ML. So hopefully now you have understood the perceptron algorithm, and you have understood up till now that it works. We may need more iterations than 4 in a complex data set, but right now I showed you for this particular data set, in 4 iterations it gets to this L4 algorithm, L4 hypothesis, which perfectly separates the two classes. So the perceptron algorithm works, but still your question would be that why does it work? So you have understood some basics, but your question would be that in this algorithm I have understood everything, but what about these update steps? What is the intuition behind these? Who came up with this? Why does the perceptron work with these update steps? So there is no other lecture or presentation which gives you a flavor for it. and I'm going to attempt to do that in the last part of this lecture. So in the last part of the lecture, I'm going to attempt to show you all the exact intuition behind adding yi while updating theta. So what I'm going to show you right now is that in the perceptron algorithm, when the current hypothesis makes a mistake, such as here, the theta is updated by adding yi into xi to it, right? Now I'm going to show you why this is the case, why this works, and I'm going to show this to you geometrically or visually. So let's again draw this x1 and x2, and let's say this is my origin, 0 comma 0. Okay, and now I'm going to show the data points very similarly to like what we had here. So we had three negative data points, something like this, and we had three positive data points which looked somewhere like this. And let's say that my current hypothesis is this. Let's say this is my current hypothesis L1, and I'm going to focus on this particular point for the purposes of this visual demonstration. This I'm going to call xi, and its coordinates are 2 comma minus 1. This is the normal to L1. This is the normal n. So one thing which we already see right now is that at this stage, this point xi lies on the other side of the normal. So our hypothesis is going to classify it as minus 1. So our hypothesis is going to make a mistake. Okay. And so we will need to update the theta, or we will need to update the hypothesis, correct? But now let's see what this updating actually means. So if you see the correct hypothesis will be something which looks like this, right? The correct hypothesis is something which is oriented this way, correct? Because if the correct hypothesis is this, then it, or if the final hypothesis looks like this, then it classifies the point perfectly. So this is the final hypothesis. So for L1 to reach my final hypothesis, is somehow has to rotate towards the right hand side. It somehow has to rotate towards the right hand side, correct? um, that is the first intuition I want to give you guys. So to update theta, the first thing which we need to keep in mind is that to classify this point correctly, L1, which is the current hypothesis, it needs to rotate to the right hand side to reach this final. Okay. One more thing to consider is that let me draw the vector between the origin uh, and this data point x1. So this is the vector between the origin and the data point x1, and this is the normal vector. The angle between these is an obtuse angle A. Now, since the angle between these 2 points is obtuse, the theta transpose into xi is less than 0. Remember, theta transpose xi essentially represents the angle. If the angle is obtuse, then theta transpose xi is less than 0. And since theta transpose xi is 0, is less than 0, our hypothesis is classifying this as negative. We want, so whatever our theta is, which is, let's say, call it theta nu, which is the theta in the next iteration, we want this to be greater than 0. Essentially, and when will this be greater than 0? When this L1 rotates to the right hand side, it rotates clockwise. It rotates clockwise so that the angle between the normal and this this vector to the point xi is acute angle. We need the angle to be acute. Right now it's obtuse, as you can see here. We need this angle A to be less than 90 degrees. So the normal vector, so look at where my hand is pointing. The normal vector should move like this. The normal vector should move in a clockwise direction. And that will make sure that theta nu transpose xi is greater than 0. So we need to rotate this line, this L1 line, in a clockwise manner, correct? Now let us see what will the effect of adding yi xi do. So let's say, as we saw in the perceptron, let's say theta nu is equal to theta plus yi into xi, correct? For the point which we have xi, the yi, which is its true label, is equal to plus 1. So theta nu will be equal to just theta plus xi. Now let us evaluate what theta nu transpose xi is. So then theta nu transpose xi will be theta transpose theta, okay, will be theta transpose xi, will be theta transpose xi plus xi transpose xi, and this is actually equal to the magnitude of xi square, so which is always a positive number. So adding yi xi actually is making sure that we are moving in the positive direction. Remember, theta transpose xi is negative, and for this point to be classified correctly, we need the normal to rotate clockwise, which means we need theta nu transpose xi to be greater than 0. As we can see, theta nu transpose xi is theta transpose xi, which is the original negative value, plus a positive number. That's why this yi into xi is added, because we are essentially making theta nu transpose xi more positive by adding yi into xi. In an essence, what yi into xi is doing is that it's rotating this normal clockwise. It's rotating this normal n. So let's say the normal n is right like this right now. It's rotating it clockwise so that it will come somewhere here, and then the angle between this and the x vector will be a positive angle. So let's say if this n rotates a bit clockwise, let's say n rotates clockwise and comes here. Now look at this angle. It's acute, right? This is what we want. Essentially, adding yi xi is doing that. It's rotating the current normal vector clockwise. So our new hypothesis will be somewhere in the rotated direction, somewhere around here. And then maybe in the second iteration is not perfect, but in the third iteration, it will rotate further and it will try to reach the correct final value. This is the actual intuition behind adding the yi term. And let me draw the uh, final thing more precisely here. So let's say this is my origin, and this is my theta previous, okay, and this is the point xi. You see the acute angle here. That's a problem. Now what I want is that I want to move towards this theta nu. So let's say my theta nu is this. Theta nu is this. Sorry, this is normal actually. So here I am showing the normal vector. Let me actually draw this again. So if I draw this again, it will look something like this. This is the origin, correct? This is the point xi, and this is the vector to the point xi. And the current hypothesis looks something like this. This is the current hypothesis. So this is theta previous. Uh, and I will draw the normal vector to the current hypothesis. The normal vector is this. So there is a obtuse angle. And now theta nu will be something like this. It will move in a clockwise direction. So this is theta nu. This is theta nu. So essentially what is happening is that This initial normal vector is moving in a clockwise direction, and now the normal vector will come somewhere here. So what that addition of yi xi is doing is that, let me write it down. Rotation addition of yi xi to theta previous rotates it in clockwise direction. It increases the value of theta transpose xi. Remember that this is negative initially, so it increases the value, tries to make it positive, so it nudges it in the positive direction, tries to make it positive, and hence it tries to have the correct classification. So in summary, the theta nu, which will be the updated theta, in summary, theta nu transpose xi will be greater than theta transpose xi, and hence yi times theta nu into xi will be greater than yi times theta transpose xi, since yi is just equal to plus 1, and this is closer to being positive. This is more closer to being positive, and hence we are actually moving in the correct direction through these updates. This is the physical or the geometric intuition behind why do we add uh, yixi here. So the reason yixi is added in updating theta is if our current hypothesis is making a mistake on xi, we need to rotate it clockwise. If xi is positive, if the yi corresponding to xi is positive for the example which we saw, we need to rotate it clockwise so that it starts becoming better, so that it starts making correct predictions. So what this is actually doing, the intuition behind this is that this is just a rotation. This is just the rotation of the hypothesis. And that's the beauty of this algorithm. If you really try to understand it, there is a lot of it going behind the surface. It just looks like 9 lines of code, but this lecture is now more than 1 hour. So to explain every single thing, I needed this much time. First we needed to understand this step. What does this product mean? We saw that it actually corresponds to the classifier making a mistake. So if the classifier is making a mistake, we need to rotate the classifier so that the mistakes are corrected. This is what the perceptron algorithm is doing in a nutshell. So if you are in an interview and if the interviewer asks you what the perceptron is doing, you can say that first it checks whether the hypothesis is correct for each point one by one. If the hypothesis is correct, it does nothing, goes to the next point. If the hypothesis is wrong, it rotates the hypothesis so that the classifications are eventually correct. That's it. This is a beautiful machine learning algorithm, which is one of the oldest ML models, and it learns on its own. I hope students you understood this comprehensive lecture which I created to explain one of my most favorite machine learning algorithms, which is the perceptron. Now that if you understand this lecture clearly, all the new algorithms which you see are kind of doing similar things, not exactly, but they are also learning from their past. I highly encourage you to write down things wherever possible so that you don't forget it and you really understand the learning process, especially these 4 iterations which I did. I highly recommend that you write these 4 iterations step by step. Okay, so this really brings us to the end of the lecture. Thank you so much for watching. And in the next lecture, we will code the perceptron. We will write a code uh, We'll write a code and we will see how the line actually changes in front of our eyes. But to understand the code, you need to understand the fundamentals, you need to understand the theory, you need to understand why the algorithm works the way it is moving, and works the way it is working. And if you write this down on your own, right, you will spend some time with it. Spend time constructing an example of your own, spend time seeing how the hypothesis line rotates by addition of this yi term. And once you spend time like that, right, you will start getting comfortable with the subject. Thank you so much, everyone. Thanks for following and supporting me. As always, I'll make lectures in a highly comprehensive manner like this, so that there are no gaps. I'll make sure first I understand everything and I write down in front of you so that you also understand everything. I could have easily right now just gone through the lecture notes and just showed you what we are doing. But that won't convey this algorithm to you clearly. And that's why I took practical examples to explain it to you. Thank you so much, everyone. I'll see you in the next lecture.